I'm a little surprised to see so many faces here because SELinux is not the fanciest or flashiest topic, but it's a really important topic, and so I'm really glad to tell you about it today. So this is Understanding SELinux for the Win. So before we get started, let me first ask you all a question. So who here, raise your hand if you have heard of SELinux before. Okay, that's pretty much everybody. All right, raise your hand if you have disabled SELinux on a system. Also pretty much everyone. So that's pretty much the reason why I have wanted to put this talk together, because I also have disabled SELinux. I've been frustrated by SELinux, and we don't need to be frustrated by SELinux. It's really a tool to help us, and so the better we understand it, the better we can administrate high security systems and be secure, which over time is just becoming more and more important. Linux is a great, wonderful operating system, and it's made even stronger and even more secure with SELinux. So a little bit about me. I've been disabling SELinux for a long time. I have a long history of doing that. I've been disabling SELinux successfully since 2002. I stopped in 2015, which is the same year that I started really working with SELinux and learning more about it. Pretty much before that, all I knew how to do was turn it off. So I love free and open source, and just working in the ecosystem is a wonderful experience. Using free software is an amazing thing, so that's part of what brings me here. I'm a principal software engineer with Red Hat since 2015, and it's a great company that I really enjoy working for. I work on a project called Pulp, along with Michael Hrivnak, and Pulp, just real briefly, is a software repository management system which manages things like RPMs and Puppet modules, Python packages, OS trees, Docker containers, a bunch of different types. It helps you sync down these packages, store them, compose them into repositories, and then host them to all of your machines. So that's a little bit about what we do on my day job. And it's actually that day job that got me working with SELinux, because Pulp needed to basically be integrated with SELinux. It needed a policy for it. So it's kind of through that work that I had to learn the hard way about how to write policies. So I wrote 3 SELinux policies for Pulp, so that's kind of how I learned a lot of these things. And I contribute to a couple different open source projects. You'll see what I contribute to if you look on my name on GitHub. All of these slides are available at this QR code, and then again at the end of the presentation, there's another same QR code along with a written link to all the materials that you see presented here tonight. So a little bit about the agenda. I changed some of the language just a little bit, but this is what we're going to be going through. I'm going to really try to motivate the problem, because understanding what SELinux is here to do is what you're going to need to go the distance to work with it. So we're going to try to motivate the problem a little bit. We're going to talk about how it works and where it came from. We're going to look at what an SELinux policy is. We're going to look at some SELinux tooling, which is kind of a practical guide to administrating it on a day-to-day basis. I'm going to try not to have a very theoretical presentation here, so we're going to look at some practical administration stuff. And then we're going to talk about this thing called the CIL language, which is the Common Intermediary Language. And we're going to finish with some SELinux troubleshooting, which I'm sure you'll have a chance to do in the near future. This is, please feel free to raise your hand or ask a question at any point during this talk, because SELinux is a pretty dry subject, and if you want to learn more about a particular part, or if you have a question, just ask it, and that'll be fine. All right. So with all the preamble stuff complete, what do you think the most common query is on a search engine like Google with the term SELinux in it?
The first 2 words, disable.
What is SELinux? I heard disable SELinux. Disabling SELinux is by far the most common search query. You can look it up yourself in the Google Trends by a lot too. So when people want to know about SELinux, they mostly want to know how to turn it off. If this talk is successful, you will never have to know this query because you'll know how to work with it while it's on. So a little bit about Unix permissions. I mean, this is a Linux meetup, so I'm not going to go over these topics in any detail. But we have to ask ourselves, why are the normal Unix security model that we know and love, why is it not enough? And we're going to look at that question. So a quick review of what it is it's a user and group model. You have users and groups, and this membership allows you to do certain things. There's this permission model, permission mask with read, write, execute, and a special bit for things like set UID. And all these concepts together make up something called the discretionary access control, or the DAG. So discretionary access control is part of the kernel. So when you try to read a file, instead of just opening that up on disk, it asks the kernel, is this user who has this group membership and trying to access a specific file, are they allowed to or not? And the kernel inside of it has this part of the kernel called the discretionary access control module. And it's built into every kernel. It's been there for a long, long time. And it's what creates this kind of user group, this security model that we're all very familiar. So my point here mainly is it's in the kernel, and the kernel is what's enforcing security. Now, there's also this kind of all-powerful root user, and that is great for, I guess it was enough in a lot of cases through the history of Linux and things like that, but there are a lot of problems with root, and let's talk about some of those problems. Actually, we're going to come to that in a minute. So one other thing to know about Linux is inside the kernel, there are all of these permissions. There's a whole bunch of them. These are just two little simple examples. So the ability to allow a user to do a reboot, or the ability to bypass file permissions. This is basically a privilege that when you make a call into the kernel, if you have this kernel privilege, you can bypass the discretionary access control module, right? So there's a whole pile of these things, and my point in explaining this is that the discretionary access control doesn't do a good job of giving you fine-grained control. Linux at the kernel level has this really rich, very fine-grained permission model, and this, the ability to do root either, allows you to do everything. Either allows you to do everything, or you're in user space and you really can't do anything. And so it would be great if we could better leverage these permissions that are in the kernel. All right, so what's wrong with root? You have to trust root. You have to trust your sysadmin. And maybe that's a fine thing. Maybe your sysadmin's a great person and they're very, very trustworthy. But I prefer to live in a world where you don't have to trust. You don't have to just trust a person. You don't have to just trust your administrator. And when you're working, if you are signing into a box with a lot of different users in it, a very large system, there are probably a good amount of people who have access to root, right? And so what guarantees do you have as a user that your data is private? What guarantees do you have as a user that your applications are exactly what you think they are? And for most of us, this isn't a problem. It doesn't keep us up at night. But part of what SELinux tries to do is it tries to make it so that you don't have to trust a particular root user, because when SELinux is enabled and configured in certain ways, you can be guaranteed that at the kernel level that they are limited in terms of their ability to access your data or access your applications. And when you work in a very secure environment or a very large environment, that's a great thing. You don't have to just trust someone. You can have confidence because you know the way that SELinux works, and there are standards about being enabled and all those kinds of things. So there's also this all or nothing security model. again, root can do everything without something like SELinux. And if say also the root user gets compromised, I mean, maybe your sysadmin is a great person and that's wonderful, but what happens if root gets compromised? It happens. And in those situations, you want some kind of, you want the root user to also be constrained and limited in terms of its ability to affect you. Things like sudo controls help out with this in terms of which users can run which commands to become root, but it's still kind of an open problem. And these are the kinds of reasons why SELinux was created. So there's another problem, and this has to do with application trust, so trust issues. CVEs happen, 0 days happen, and without SELinux, you have to trust that applications are secure. You have to trust that the things that are running are exactly what the original application authors intended, right? But when applications get compromised through CVEs or 0 days, then all of a sudden, whatever that application can access, all of a sudden now a hacker can access. And so SELinux is going to come to the rescue, and we'll see how in a little bit. But you also need to trust that the apps are configured correctly. So a lot of, for instance, like with PHP, I've heard a story just last week. The php.ini was not configured correctly, and someone uploaded a malicious payload and was able to, through the PHP application, drop into a user shell on the machine. And so this is a configuration error, and these kinds of attack vectors are also stopped in some cases by SELinux. And there's also a trust problem that has to do with malware. So this is a different kind of an issue. You have to trust that the application developers itself don't have a malicious intent, and really SELinux does not help you here. This is the one thing that I wanted to point out. So if you download an application and it's nefarious, SELinux is not going to save you. It is not magic. But what are some great ways to mitigate that attack is to use open source software, to use packages that are signed so that you know they came from who you think they came from, to use reproducible build systems so that way you can build something yourself and compare it against the binary that you received from a signed package from someone else, and you can verify that they're the same. And so that's kind of why you hear a lot about reproducible builds, which is kind of a hype, or an important, it's not hype, but it's an important buzz area today. And also open build systems. I mean, you have to trust somebody, right? And so I choose to trust open build systems versus closed build systems because I can have some more confidence in understanding kind of all the bits that went into the packages that I use. So I'm pointing this out as an area that SELinux does not necessarily resolve for you. All right, so when apps get compromised, bad things can happen. Who here has ever, let's do another little show of hands, who here has ever been running a system and had an intruder that has compromised your system? Okay, that's maybe like 15, maybe 20%. I bet there are more of you who have had this, but you just do not know that. And that's the thing, it can be hard for us to know as sysadmins if the systems that we're really running have been compromised or if they're secure. And the thing is that SELinux, when properly administrated, can be an amazing intrusion detection system. In fact, if you're running SELinux and it's well applied and well configured, if you're getting compromised, first off, you probably won't. But secondly, if you do, you will probably know almost right away, because they're going to try to do things on the system that's going to create denials, and we're going to look at how some of those work here in a little bit. But applications get have CVEs and also just regular bugs that allow intruders to get further than they should. And so, for instance, Skype had a CVE that allowed all of the data had its permissions changed to 666, which allows everyone to read that data. So now everyone on the system can read your private Skype data. It's just one example. There's also kernel exploits. So if an intruder can get on your system deep enough to have shell access, as a user, not as root, but if they can have shell access, then that's an opportunity for them to then try to do some kind of kernel exploit, to exploit the kernel directly. So layered security here really helps us. If you can keep them out of user space, then you can keep them from having an opportunity to attack your kernel. But there are privilege escalation exploits out there, and so that's one of the reasons why SELinux is great. It prevents these kinds of things. When your apps get compromised, they can install backdoors, and this is the thing. I'm pretty sure, statistically for the people here, there's a backdoor in somewhere in one of your systems. Almost certainly. Question is where and if you know it or not. You can make network connections. You can become a DDoS slave. So that's what happens when your app gets compromised. And if your app is root and it gets compromised, it's pretty much game over, because you now are, the attacker now has root access. So without something like SELinux, you're totally screwed. So a little public service announcement. Don't run an apps as root. Don't do it. Sometimes it's convenient to do it. Don't do it, because these are the kinds of security implications that come from a decision like that. All right, so that was all literally the motivation section, because I think it takes a strong understanding of kind of why you would want something as frustrating as SELinux in order to want to use it and learn it. But enough with the preamble. So Security Enhanced Linux is the full name for what is called SELinux, and it's a security mechanism that is built into the kernel. It's been part of the mainline kernel for a while, for years. I forget the exact kernel version that it was introduced in. For a while, it existed as like a patch or a module, a kernel module that you could build separately and load into your kernel. And a while ago, several years, it became part of the mainline kernel. So it's a security mechanism, and it brings improved and enhanced security for your system. So here, I'm going to step over here a little bit. So here, this is all user space up here at the top, and when you perform an operation, it'll call into the system call, so down into the kernel space, which is below this black line. And it'll check if any errors have occurred, so it'll exit. And then here, this is the normal DAC checks, the discretionary access controls, so controls to check if, basically the POSIX permissions and the user group security model. So that's enforced here at this level, because if you can't pass the discretionary access control, then here, discretionary access control, then you're just denied. So this is the new part that came with the SELinux introduction into the kernel. So when you load the kernel module, it's this LSM module, which is the Linux security module, very generic name. But this is the thing, the code base in the kernel that provides SELinux enforcement. So your call goes through here, and this is configurable. And so there's this kind of other section here where it says, okay, the user is doing this thing, and we'll talk about how that's expressed here in a minute. The user is doing something, let's look into the policy that's running on the system, and let's produce an allow or a deny. And that's what SELinux does. It takes these policies, and as events occur on the system, it says, oh yes, allow this, it is allowed, or deny this, this is not allowed, and log. So from that decision, if it's denied, then it says, no, you're denied. And if it's allowed, then it's allowed. So it's from the Linux document, the SELinux documentation. So in SELinux security, there are file contexts. So this is our first look at a little bit about how SELinux actually gets its job done. So every file has a security as a file context. And this file context is stored as an extended attribute. Thank you. Yeah, thank you. This file context is stored as an extended attribute on the file itself. So you can see them on your own system. If you have a Linux system or you're fooling around with one, feel free to with SELinux enabled or on or loaded into the kernel, you can run this git fadder command, which will show you the file context, the SELinux file context that's stored with the file. So like if you move the file, that file retains its file context because it's stored actually with the file. And so here's a look at the bottom. Well, this is some output from my computer, but here's a look at one of the file contexts here. So this is just kind of an impressionistic look because we're going to look at the anatomy of one of those here in a little bit. But this is the file context, and it's a label for a particular file. And it's used by SELinux to make a decision around what are the permissions that should govern access and attributes of this file. Any questions so far? I haven't gone through much detail. Yes?
You said that the attributes are stored with the file. Is that part of the inode of the file?
Yeah, so the question is the label stored as part of the inode, and is it file system dependent? It is stored as part of the inode, and I'm sure there are some file systems that it will not work with, but generally most of the file systems that I've encountered allow the storing of extended attributes. Certainly the ext3 plus line does. Other questions? Okay. So this is a SELinux domain. So each process, all right, on your system has what's called an SELinux domain, and if you list them with the capital Z flag, like here, then you'll see, along with your normal PS process listing output, you'll see a domain for that particular process. They call it a domain because that's the word they use to describe processes. But when you look at the label, some people call it a process label, it kind of looks like a file context label. So here in this example, you can see here. So I'm looking at the process output for system D, journal D, and it has this label here, which is what you get with the capital Z flag on PS. And it's a little hard to read there, so I included it down here. And look, this is very similar to the other label that you saw on file contexts. And we're going to analyze these here in a minute, but the idea is that they're labels, right? So there's a label on your process, there's a label on a file, there's a label. There are those kinds of labels, and then SELinux is reasoning about, from the policy, whether this process label can do something like an action to this file label. And since everything in Linux is a file, like file descriptors are files, and network sockets are files, and devices are files, this kind of file labeling, process labeling technique allows us to have a richness to govern pretty much all aspects of the system. All right, so let's actually dig into what these do. This is an anatomy of a file label, so the first kind that we looked at. So here there are 4 types. I'm trying to stay close to this microphone for the recording. So there are 4 types and 4 aspects to a particular label. There's the SELinux user, there's the which is the user that SELinux thinks of. That SELinux thinks of that file as being owned by. There's the SELinux role, which is kind of like a grouping model, or it's kind of like groups for SELinux in a way. And then there's the type, and these 2 I kind of skip over a little bit, because the truth is that if you're just getting into SELinux, almost always, the thing that you just need to look at is this one, the SELinux type. This is the one that is really defining in most usage, in like 99% of usage, what is important about this particular file. So here it says password underscore file underscore t. And that's just a string. Now, it's named something that's like human readable and kind of helpful so that it's, well, this is a password file. And indeed, this is the output from the password file. And the SELinux policy that's associated with the password aspects that govern and manage that file and processes that talk with it, they've chosen this label, password file t. A lot of SELinux labels have this underscore t on the end of it, and that's a common convention for targeted mode of SELinux, which we'll talk just a little bit about later. There's also the sensitivity level. A lot of times when you read about SELinux, you'll hear about something called the MLS model, the multi-layered security, which is really fancy, pretty awesome way for to define like rings of security, kind of like, you know, unclassified, secret, top secret compartmentalized, and they're kind of like, it's a range security model. And so the whole idea there is to prevent data from flowing from more secure aspects to less secure aspects. They, even in introductory resources, they talk a lot about this, but you're really not going to do MLS stuff unless you're, frankly, if you're doing MLS stuff, you didn't come to my talk. So the last part there is the sensitivity, and that's used in MLS environments to describe which ring you're basically at. Okay, next. This is a, let's see, let me go back. Okay, so this 4-tuple option, these 4-tuple descriptor is used, like I said, by processes and files. And this anatomy, SELinux user, role, SELinux type, and sensitivity are the same for processes and for files. And similarly, the SELinux type, especially for the purposes of your usage, and mine, is pretty much, that third one is the most important one. That's the one always to look at. So next, let's look at a rule. So this policy, if we go back here. So if we go back here, this is the policy area. So you've loaded like all these rules into this box. And so on any given system, the question is, well, what are the rules that are running that let me make a yes-no decision, allowed, denied decision, based on the process label and the file label? So what a rule looks like is kind of like this. It says allow versus a label like deny, or a word like deny. Allow this process, user underscore t, to when it is trying to do a read operation, so that's the permission, when it's trying to do a read operation on a file system with basically a file that has this security file context of bin underscore t. And objects have different classes is what they're called in SELinux. And so a file is a type of class, a directory is a type of class, a socket is a type of class. And these are kind of groupings that SELinux can reason about. So when you see this rule, it's basically saying allow the process labeled with user t to be able to read a file that's labeled with bin underscore t. Any questions about that? Any questions about other things? No, okay. All right, so you can see these rules on your system. You can use the sesearch command, which is a utility that will help you show all the rules that are loaded into your system. And when you install an SELinux policy, these rules basically get loaded in. And so one of the first ways that you can ask your system questions about, hey, what's allowed here? Or, hey, I have a file here. What kinds of things can do things to it? Which kinds of processes labeled which ways, and what can they do? This is a way for you to look at that. And you can see here, so this is a more, well, they're both real examples, but it says allow HTTP DT. So that would be the HTTPD process, which when you're running with SELinux becomes HTTPD_T, allow that process, the process with that label, to do all these things: IO control, read, get attributes, lock, execute no trans, which we'll talk about later, and open. Those are all the things, all the operations that are allowed to be used when a process with this label is trying to do one of those to a file with this label. And so when HTTPD loads its policy into SELinux, it's defining the HTTPD_T process type. It's defining file system contexts, and it is applying those labels onto the different areas of the file system that HTTPD wants to interact with. And that's a look at SE Search, which you can use to learn more about your system. All right, so where do these rules come from? They come from SELinux modules, and each module defines a collection of rules. These SELinux modules, they're compiled. SELinux, since it works down in the kernel, compiles the rules and kind of loads them into the LSM module. I guess M is for module. So when you start a Linux system and it has SELinux installed on it, you've got a bunch of modules on there. And so your system is already, prepared for you to learn more and to interact with the security model that's already in place. I mean, any distribution that you're running today, well, not any distribution, but many distributions come with SELinux ready and prepared. So you already have a bunch of these on your system, especially if you have SELinux turned on. So applications bring modules too. So we just looked at an HTTP example. There's an HTTP SELinux module, and when you install it, it creates that HTTPD_T, and it creates all the different file context labels that it needs. So things like HTTPD_temp_T, which just from the name, is a temp file that HTTPD will use. So when I wrote the modules, with some help from others, for Pulp, we wrote 3 different modules, and we shipped that SELinux policy with our application. And so, as was discussed earlier, next week, next Thursday, we're going to have a hack night where in Durham at Cactus, and as a time for folks to come by and play around with SELinux and learn more about it, or you can try writing an SELinux module, and I will teach you how to do that, from a very basic one to a more advanced one, for an application that currently does not have one. Or you could come by and we could try to fix an SELinux bug, which usually boils down to, the kinds of bugs that I would help fix are user space bugs, where a particular application is just, there's an error in the policy, and it's not working correctly in some situation because the policy is deficient. And so next Thursday is a time for us to kind of write and play with some modules. So these applications bring their modules, and any application that is ready to work with SELinux has already defined a policy, and they ship it with their application. So we wrote a policy for Pulp, for instance. And your SELinux policy on your system is the sum collection of all of the installed modules. And you can list those modules with the SE module command. So this is a little snapshot from my system. And a little later, we're going to fool around on the terminal some. But this is just the very first little bit of the list of modules that I had running on my Fedora 24 system. So we'll look at some of these modules a little bit later. Any questions so far? Yes?
So, you've been talking about SELinux in the context of the user being the user on the box and being local to the box. One of the advantages of SELinux is that you wouldn't have to be, you'd be running a server and be accepting remote users. And now what you have to do is maybe run a pluggable authentication and have that user's level of credential be assigned to the application that's running the program, to then have that security level be utilized when it goes to access, I/O control or access to files and stuff. Have you been speaking about that yet? Or, because I haven't heard you get into that topic of the module or the application taking the level of security of the remote.
Yep. So that's a great question. So the question was, what about situations where you have a multi-user system and you want SELinux to reason about what should be allowed or denied on a user-by-user basis, which is a great question. So far in my talk, I have not covered that. And I would be happy to talk a lot about that with folks. It's an important, this is definitely something SELinux allows and enables. And there are some additional labels that you can apply that help govern this, which, for instance, just to talk through a little bit of an answer, because there's not much content here for it. So the way that works is when the transition, when a user starts a process, earlier it was being labeled as HTTPD_T. Well, when you layer on this kind of user knowledge, when user A and user B both launch a process, they receive different labels. They're still labeled as HTTPD_T, but they have additional, there's basically more to the label at that point. There are more things because it's still that for tuple, but two different users launching a process will end up with that process running with two different labels. So this allows SELinux to reason about data that's owned by user A is only readable by a process that was launched by user A, and similarly for B. Does that help answer it? In an impressionistic way? Yes?
You mentioned Hacknight and fixing potential bugs in SELinux configuration that you have. Is it possible to put reward the system so that you can root commands, fix the SELinux policy using what installed out?
Yes, you can definitely end up in a situation where, I'm sorry, the question was, can your SELinux system be so twisted up that you are locked out of the ability to fix it? And if you have the ability, if you have physical access to the box, you can still fix it, generally. What you would do if you were totally screwed is you would end up rebooting the machine and disabling SELinux from being loaded into the kernel. And this is why physical access is an important aspect of computer security. So at that point, you would be restarting the machine without SELinux running, and you could relabel, for instance, the file system to correct a file labeling problem, which might be the thing that stops you. You could also adjust the policies that will be loaded on the next boot the next time SELinux is enabled. So you could, pretty much fix it through those kinds of draconian methods. Is that good? Any other questions? I love questions. All right, raise your hand if you're still awake. Okay, most of you, that's great. Okay, having file context get assigned. So policies have these .fc files. An SELinux policy is 3 files. We're not going to talk about those today because this is kind of more of a sysadmins focus about how you can work with SELinux and stop disabling it. That's really my goal. So how you write files and how you compose them and author them. We're going to cover that next week. There's going to be like a little mini, like a very short 10-minute presentation, like a hello world for an SELinux module. So all I'll say today is that one of these 3 files is a .fc file, the file contexts. And this file defines which portions of the file system will receive which labels. So when you install a particular SELinux policy, its fc files will be determining the labels. And SELinux remembers these, and it keeps them internally. So for any given file in the file system, SELinux can say, oh, well, I know you, file. I know that you're supposed to receive this particular label. And you could imagine that two different policies could both claim ownership over a particular file because it allows for like wildcards and things like that. And so there's a very clear conflict resolution order for conflicting rules. And it's generally it goes from more specific rules override less specific rules. So if one rule has an actual full path to an explicit file, and another rule is a partial path with a wildcard star on it, the more specific one is going to be considered to be the real label. So new files are automatically labeled because SELinux knows about these files, and so when you create a file on the file system with SELinux enabled, it automatically shows up with the right label, and it's because the policy engine inside of the kernel knows, oh, based on the path, it should have this particular label. Moving files does not automatically relabel them, right? Because it's stored in an extended attribute on the file, and SELinux doesn't get involved. So if you're moving files around, for instance, if you make files in your home directory, you'll get something like unconfined_t, which is a file label for a file that's in your home directory when you're in targeted mode. Gosh, that's a complicated statement. We'll talk about targeted mode in a little bit. So if you create it in your home directory and then you move it, say, like into the place where HTTPD is serving out of, and this is like one of the most common problems that people experience practically when using a system that has SELinux enabled. Since you created them in your home directory, they got one label, and then you moved them, they didn't get relabeled because SELinux doesn't interfere unless it's a new file, basically. So the fact that you're moving the files means that they'll be in the right place in the directory structure, but they won't have the label that HTTPD expects. And so at that point, when your web server is running, it has the process label HTTPD_T, and it goes to read out of the area that it expects to find your website in. It's going to say, oh, wait. Well, really, SELinux is going to say, wait, you can't read these. This process does not have an allow rule to read that type of file, deny. And so be aware as you're moving around files on an SELinux system because you might not be updating the file labels the way that you need to. So you can see all of the expected labels, basically the bid directory of knowledge of a running system inside of the, for instance, that path. It might be different on your distribution. This is on Fedora 24 system. And for example, here's a look at what one of those FC files looks like. And then I'll come to your question. Here's path, user bin celery, and gen context. This is an SELinux idiom that you can learn more about next week when we actually talk about the policies and writing them and writing SE files. But it basically says generate the idea of a security context that has system U, object R. These are very generic labels. When you're running in targeted mode is the most common mode that SELinux has, and we'll talk just a little bit about the modes later. But for instance, MLS is one of the other modes. So this like multi-layered security model. So targeted mode is kind of like SELinux, the simple version. And these two, system U and object R, are the labels for the user and the role when you're in targeted mode. So they're very generic, and that's why we don't really pay attention much to them. But this file, user bin celery, receives this label, celery exec t. So this is a little snippet from the Pulp policy that we have worked on. So, question?
So, how do things affect the way that the absolute path differs depending on either if you're a changer or if you're a doc or if you're following a symbolic link? How would SELinux understand about those and still do the right thing?
So the question was, how does SELinux handle a couple different situations, like when you're laying your file system out differently, or when you're using a root or a Docker container, and also situations where you have symlinks, for instance, in place, which are changing the paths. I'll take each one of those individually. When you're laying out your file system differently, you can apply labels to the file system yourself. As a privileged user, you can write, it's actually a permission itself, the ability to write labels or the ability to write this kind of label. And so if you're in targeted mode, the root user is able to write a particular label. And so if your data is in an unexpected place, the place that the policy doesn't expect, you would likely manually apply the label there. In other SELinux modes, like MLS security, you might only be able to write that label if it's contained in an area where you have a write access. So in targeted mode, root can help you solve that problem, but in more advanced, but it's still not a security loophole, because in more constrained systems and richer policy systems, it'll prevent that. What about things like Docker containers or chroots? It's kind of a similar answer. You're able to write the file system label, so I think that would handle the chroot case pretty well. You can also modify the way that processes transition as well to handle running a process through something like Docker. And there's some really great blog posts on this, and I'm going to kind of couch the rest of the Docker stuff on that. SELinux and Docker has been, or really not even just Docker, like containers in general, has been an area of much debate. And Dan Walsh has published some really great things on that, who is Mr. SELinux. Any other comments on that?
Well, just the question is, I didn't think that just because your system is SELinux enabled, that your Docker would then be SELinux enabled, or your container would be SELinux enabled.
Yep, so the question is that what do we expect the labels to be in a system where we're using containers? And it's a good observation, because Docker can be is a runtime environment, or really a container in general, to run a lot of different kinds of applications. And so how can SELinux know? I mean, it would see the Docker policy, and if you're running a Docker container, it's probably going to get some process label like Docker_T.
Well, plus the other thing is Docker's supposed to be running immutable objects. So if you're in an immutable environment, you don't care about security as much, right?
So the comment was Docker's supposed to be running an immutable environment. So how much damage could we possibly do? I think when people really run Docker, they often run mutable environments, the kind that can change. And so they say that you should run them only immutable, but in practice, I see so many people making mutable Docker environments. There's some great, you could more finely control the way that particular Docker container is being transitioned, to take the personality of more like what the original application is. So if you're running HTTPD inside of a Docker container, you could control it and configure it so that when it launches HTTPD, that the Docker container itself takes on the personality of HTTPD in terms of how SELinux thinks about it. That's kind of like a high-level answer. Go read some of Dan Walsh's blog posts on the matter. SELinux and Docker is a pretty hot topic. I believe there was a comment there.
Yeah, you pretty much already said what I was going to say, that if your file system is laid out differently, that's when you want to write your own policy. That will take care of that new layout of file system.
Yep, so the comment just for the video was when your file system is laid out differently, or when you need your processes to transition differently, you can adjust and update the policy for your particular box. And the content that we're going to look at towards the end, which is, will show you literally how to do that. It's a lot easier than you would think. Yes?
I wanted to kind of go back to where you were talking about the very basics, where HTTPD tries to read a file and it looks at the context and it's not right.
denies it. So how are you going to know that? Is there some sort of debugging and logging?
So the question was, how do you know when a denial has occurred? Say HTTPD, the process is trying to read a file that has an unexpected label that it does not have an allowable access to. You're going to know because it's going to be logged, and we're going to show those logs here in a little bit. And we're also going to show how to interpret them. So we're going to come to that. Other question? I love the question though. Yes?
You mentioned moving the file doesn't relabel it. What about copying a file? What kind of label does the copy get?
Yep, so what about copying a file? What kind of label does the destination receive? It's considered a new file from the file system perspective, and so it receives the label according to this automatic labeling that occurs based on the sum total of all of the file system label rules that are kind of things like this, and including the resolution of any conflicts that occur to two file system labels asserting ownership over one particular file. So it's considered a new file, and it's automatically labeled based on its location. Does that make sense?
Sort of. Probably will make more of it.
Okay, very good. Yes?
Analogous to that question, is there a way to copy files to keep the labels intact?
Well, generally for SELinux, you want the destination to be automatically labeled because if it's living in a particular area of the file system, all the policies that are loaded on the system probably know what the right label would be for that. So for instance, if I copy my website files out of my home directory and I copy them into the place where HTTPD is serving out of, you probably want them to change labels. And so what you generally want to do is let SELinux apply the labels that it knows about. Now, you can also copy labels and tell SELinux to stay out of it, and you do a copy with preservation of extended attributes, and we'll look at that here in a little bit. All right, great. I love the questions. It makes it more fun for me. Okay, so these are some utilities. Again, this is kind of designed to be a little bit of a practical guide, not such like a theoretical thing. So these are three different utilities and one technique that you can use to ease the burden of managing your file contexts. So restoreCon basically says you say restoreCon and then a path like restoreCon with verbose mode, some file, and it will tell SELinux, hey SELinux, this file, relabel it according to what you think it should be. And it looks through its policies and all the conflict resolution of the different labels, and based on its location in the file system, it determines which label should be applied, and it applies it. And so, like, look at this move example. If you create files in your home directory, they get unconfined, file T as its file system context. If you move them, preserving their attributes, to where the web server reads out of, you're going to get a denial. And then you say, well, how do I fix that denial? Well, just tell SELinux to relabel the files, and the utility restoreCon is exactly what that's for. So it's a way to apply labels based on SELinux's knowledge, so that you don't have to think too hard about what the right label is for it. So, of course, if you know what label you want, and you can use ChangeCon to apply a particular label. So for instance, you can ChangeCon recursively to apply this file system context, HTTPD syscontent T, which is a real label for HTTPD web content, basically, system content, to the directory /web/. And so this is an example, like if you've configured Apache to serve from /web/, which is like not the default place, the normal HTTPD policy won't know that, oh, files in /web/ are supposed to receive the label that would allow them to be read by HTTPD. So as an admin configuring the system, you could manually apply that label and then a process with the domain httpd_t will be allowed to read that content. So ChangeCon lets you apply a label of your choice. And then fix files. Fix files lets you basically make sure for a particular SELinux policy and all the paths that are named with it, kind of like these things. So this is like one of the 3 Pulp policies, and these are the paths that are named with it, these 3. These have been celery, varcache Pulp, wildcard, so the cursor there, and then var run Pulp there. And it gets those labels, celery exec t, var run cache t, Pulp var run t. So if my Pulp system was in a really weird state and I knew that the file contexts were the problem, I could say, well, I could go through these one by one, and you could do a big restore con, but you'd have to run a restore con for each of the ones in the policy, each of these paths. Like restore con this, restore con that, restore con this. So fix files looks into a particular policy and will apply automatic relabeling to basically get the files on disk relabeled according to what the policy defines. Any questions about those 3 utilities, which are super important? Okay, so say your system is, oh yes, one in the back, thank you. That's a great point. So the comment was an excellent comment. ChangeCon does not survive a full relabel. It's a one-shot deal. So if you move your files into /web/, you apply ChangeCon, and then say that you do a big relabel, which we'll talk about there, or say that you install another policy or run fix files on a policy, which has a rule that specifies a different label should be applied to /web/. Well, it's going to do what it's supposed to do. It's going to apply the labels. And so ChangeCon does not change the state of SELinux in terms of remembering, oh, in the future, I need to preserve this change. And so that's definitely something to be aware of as you're administrating SELinux. Great comment. So I mentioned this big auto relabel. If you want to make sure that every file on your system adheres to the policy's understanding of all the policies to make sure that they have the right labels, you can do this thing where you touch at the root of your system and you create a .auto relabel using touch of just an empty file just with that name. And if you reboot your system, when SELinux starts up, it looks for this file, and it's going to take a long time to boot because it's going to literally read the extended attribute out of each and every file in your file system, check with the policy engine to make sure that it's the correct policy, and apply the label. One time I totally hosed my system with this, where I wasn't running SELinux, and then one day I said, I absolutely have got to turn on SELinux on my system. This was on my very own laptop. And so when you go from never running SELinux to running SELinux, when you make that transition, it does this for you, lucky me. And it applied this mass relabel, and then my system would not boot. I still don't know why. So, something to think about when you're enabling SELinux maybe for the first time on a large system. Make sure you take a backup. But if you, for instance, have introduced a lot of files or you've made a lot of changes and you just want to make sure that everything's good, and you can afford the time for it to check every file, this is an easy technique. You want to do this instead of doing a relabel while the system is running and all your applications are launched. This can leave you in a bad state because your system is already running and your processes are already labeled and they're reading and writing to the file system, and then you're going through and changing the labels underneath, right? What could go wrong? A lot of things. So this is a better way, because prior to pretty much user space being started and all those applications being started, the relabels will be applied ahead of time. So that's kind of the value of this versus just doing a restore con recursively from the root. Don't do that. Yes?
You mentioned backups. Do you have a recommendation for practice? Like, should you take backups, like with tar, preserve the extended attributes, or should you not preserve them and then after a restore, auto relabel, or is there something in that space that that works, or something to be aware of, some gotcha to avoid?
So the question is, what do you do about backups? Are there any recommendations or best practices around around backing up and restoring files? I mean, I have an opinion. I don't know that it's necessarily a best practice, but what I would do is I would definitely preserve labels anytime I'm backing up user data, because it's possible that there are user-to-user attributes that you want to preserve, and I think those are right to preserve and right to try to restore. Because otherwise you could lose the identity of one user's data versus another from SELinux's perspective. If it's areas of the file system that are more generic, just like application data, well, when you reinstall that application and it goes to use that data, it's going to get relabeled probably then. Or you could just say, oh, that's weird. This restored data isn't working correctly, like my application can't read it, restore con, and just let the policy figure it out. So the data is kind of contained in the policy there for system applications. So I wouldn't be as worried about those. Is that helpful? Yes?
Well, what if your data is on an NFS mount?
Oh, great question. What if your data is on an NSF mount? NSF has special SELinux integration points, and in your mount file, when you configure your mount, you can set these, and so you can set the file context that will be written for any new file. And now, if you move a file like from a local system to a remote system, if it's over NFS, that's still considered a new file on the remote system. And so that move won't preserve the SELinux context, but you can define the SELinux file context that will be written for new files on the remote system according to your export config and your mount. And so, for instance, when you run Pulp in a clustered NFS system, we have documentation that says, as an application, oh, when you're using us with NFS, this is the file system that you need, and here's how you can configure NFS to do that. Does that make sense?
But is there a single rule for a whole NFS mount?
Yeah, there is a single rule for a whole NFS mount. Okay. That is the way that feature is positioned right now. Of course, you could have a fancier policy on the remote end and outside of NFS, and you could do more with it.
Thanks.
All right, I'm going to move on. Okay, so now we're kind of moving into a little bit of the practical stuff. It's been a relatively long talk already, so got some more content, but really trying to show some real practical stuff now that I think you guys have a pretty good introduction. So SELinux, when it's on, meaning that it's loaded into the kernel, okay, because you can boot your kernel without SELinux enabled, but if SELinux is loaded into the kernel, the only way to remove it is to reboot without loading it, right? But when it's loaded, you can still change its mode. You can turn it on to enforcing, and this means that if you receive a denial, the process will be denied. Like if I'm reading data and I don't have an allow rule, I will not receive that data. The application will not receive that data. So set enforce 1 is what you should do to turn on SELinux in your system, assuming that it's loaded into your kernel. There's also set enforce 0, which will turn it into permissive mode. And in permissive mode, this is a really useful mode because denials are still logged, but they do not actually prevent application use. So the data still is readable, for instance, or writable, or whatever the permission is. This is really helpful because say that your system experiences an SELinux error, and it's like, okay, well, I'm going to write around that rule, and I'll show you how to make modifications to your SELinux system here, just as an administrator, not a policy author. But, you know, oh, I see a denial. Okay, well, I need to allow that particular kind of case. In enforcing mode, you're literally going to usually see just the first denial, and I call this the first denial problem. And the issue is that enforcing mode stops your application because usually it's a fatal exception, it's a fatal error. It can't continue because it doesn't know how to continue after it can't read the data that it thought it was supposed to read. So if you run your app in permissive mode, you'll get an opportunity to kind of see all the failures and have a better scope of the problem. So when I'm troubleshooting a system, I'll flip it into permissive mode, reproduce the problem, and then I'll have a better idea of like, oh, what are all the issues here? Git enforce is a utility that will show you whether SELinux is enforcing or permissive or disabled. Disabled is also an option. I'm not going to show you how to do that because that's already the most popular query on the internet. So that's an option you can do. Yes?
I was just going to ask, with the SE troubleshoot, is it recommended?
I'm sorry?
With SE troubleshoot package, do you recommend it, or is it actually in your troubleshoot?
Yeah, so there's a package called SE Troubleshoot. I'm sure a lot of people do use it. I don't personally use it, but I mean, yeah, check it out. SE Troubleshoot is a package designed to help you analyze and understand SELinux denials. So I'm going to actually show you some of that myself in terms of how to interpret them. But so I'd say like, you know, +0. That's a decent thing to do. All right, so targeted mode. I mentioned this a couple of times. This is kind of like SELinux simple. If you turn on SELinux for the first time, this is pretty much what you're going to get. You can set this in the SELinux config file between using targeted mode or MLS, multi-layered security mode, and there are other modes too. But everything is allowed in targeted mode, and they use deny rules to deny. And that's this is a little bit strange, right? Because SELinux is all about security, but this is defaulting to allow. But really what happens is in most targeted systems, pretty much every application that you're going to run is going to come with special file system labels and special process labels. And usually all of those applications are defaulting to deny. But what this does let you do is it lets the user kind of have full freedom and be unconstrained in terms of what a user can do. So if you turn on SELinux, for instance, in like Fedora, or pretty much any distro, you're going to get targeted mode. And if you look around on the file systems in your home directory, you're going to see it's going to have this unconfined T label and an unconfined T domain. And unconfined T is the same label that you get if SELinux is disabled, for instance, like not in the kernel, and you create a file, for instance. So this is a little bit about targeted mode. And this is what I was saying earlier, that daemons or applications, they transition into a particular process domain as governed by the policy that was shipped with that application, and that usually has a default to deny rule inside of it. So targeted mode is very permissive, but at the same time, it's still pretty darn secure. So this transition that occurs, say when you start HTTPD, yeah, the process does start as unconfined T. It does, because everything in targeted mode does. But the policy rule for HTTPD transitions that from unconfined T to the process domain HTTPDT. And that way, and that's kind of how this happens. It's not magic. It starts as unconfined T, and the policy transitions it. And when you write a policy, this is pretty much the first thing you do. And so, hack night, and it's Thursday. You can come learn more about how to write a policy to cause a transition to occur. Okay, so where are the logs? Logs are in borrowlog audit log. It's pretty much that place in all systems. And both allowed and denied operations are allowed there. Generally, I mean, you can still do things in user space that won't even need to consult SELinux. But, you know, many operations where you have to go down into the kernel for permissions will either result in an allowed or deny here. So this is a very chatty log. You can filter them for denied. You can also look just for denials with AU search -m AVC. This will literally show you all denials on your system. And here's what a denial looks like. So, who here has seen one of these before? Oh, good. So, like half, 40%, 50% of the room. All right, so I highlighted the parts in red that are, what in my opinion, the most important. So, first off, what was it doing? What was the operation that was requested? This was a get adder, so it's trying to read a file attribute. And the S context, this is the security context of the running process. So if you did the PS with the capital Z and you see the process domain, okay, you would see this. So this is this Gwibber_T process. Again, because with the for tuple, this is really the most important one. I mean, they're all important, but if you're in targeted mode, that's usually the one that matters. So then the target context. So it's the source context, that's the target. So a process with this process domain label was trying to do a get attribute on Mozilla exec T. And that's the file system context label. So this is usually what you want to run through in terms of understanding. Like, you really understand an ABC denial if you can answer all these questions. So, which process was denied access? Well, Gwibber_T. What domain type did the source process operate in? Well, actually, that is literally this Gwibber_T domain type. But the process was Firefox. The domain type was Gwibber_T. What object or subject was the source process denied access to? It was denied access to a file. And what was the objects of the type of the target? Well, one of these two is, it's a type of the file, and it had the label Mozilla exec T. Class of the target. One of these is the path. Anyways. Second line here, this path. So, really the parts in red are the middle parts that I focus on. So you guys can probably do a better job answering these questions than I can. But the item number is up there, INO, it's the item number. And this generally helps you reason about, of course, the important question, which is what really happened during this ABC denial. So this kind of gives you the information that you need to analyze one of these. There's a really good blog post on this, by the way, which answers all these questions in great detail, and it's the one attributed here at the bottom. So if you want like the full, detailed, correct answers, you can look there. So SELinux utilities, when you're administrating SELinux, generally all the utilities have this capital Z in them. It's kind of a consistent thing. So ls-z show me files with file labels. Copy, move, install. They handle file context a little differently. I think we've already covered that. Copy makes new ones, move preserves them. Find has this dash context option, which lets you search for files by context. ID supports a dash Z, PS supports a dash capital Z. So anyways, this is something you'll find very commonly across a lot of the Linux utilities. So there's SELinux support kind of baked into them. There's a question?
I wanted to ask, what was the story of that denial? What happened?
Yeah, so what really happened with this denial? Inside of Firefox, it had a, as part of like the bigger application of Firefox, it had a sub-process which was running as some application part of Firefox greater. So this sub-process name was Gwibber_T. The best way to answer what really happened is to wonder, well, what is libert? And I don't know what libert is. So, but it was trying to read attributes on Mozilla exec_t, and the exec_t idiom is very common in SELinux for a binary. It's part of how a binary transitions when it goes from just a file to a file that's running as a process. And so it was trying to do something to the Mozilla binary. Yes?
Why did the 4-tuple become a 5-tuple in this case for the S context? We've got S's and C's.
Yeah, so I don't really have a way to answer that question. The question was, why did the 4-tuple become a 5-tuple? So 1, 2, 3, 4, and 5. And this has to do with more fine-grained. I mean, the high-level answer is this has to do with more fine-grained security models, which I think the sensitivity can be reused here to become something that the policy can kind of have more control over. So it's not a great answer. They don't have a better answer to that question. So one thing I meant to say earlier is that I don't have a background in computer security. I kind of learned this like the hard way a little bit, and so I'm really, I feel like I'm just kind of like you all in the sense that just learning and trying to apply these skills. So I'll try to go learn more about that. So more of the utilities associated with this. So there's tar and zip and rsync. If you read the man pages, you'll see more options there. Okay, so there's this thing called CIL, which is new in SELinux 2.4. It's the common intermediary language. So something to know about SELinux is that it's a policy language, right? And so, of course, what happens with policy languages, people write tools to let you have higher level policy languages, which then compile down into the low level statements, right? I mean, when I showed you a rule from earlier, that was a very low level statement. And so people who work in this stuff all the time, they want higher level languages, DSLs, stuff like that. And so if you look out there, you'll see a lot of these things. And there's a bunch of high level languages for SELinux that are out there. And so common intermediary language is exactly what it says. It's a common intermediary language that allows you to take any high-level policy written in, say, 2 different high-level DSLs, convert them both into the common intermediary language, and then you can use tools like diff on them to say, okay, what's the real practical difference between these 2 things? You can decompile a policy that's running on your system into CIL using a command like this. And we will, at the end, we'll look at one of those if there's time. And it allows them to be compared with diff. All right, so SELinux Booleans. So an SELinux policy may not want to just give all the, may not want to just enable all the allow statements at once. Say that the example, of course, a little Pulp example. So if you're serving files, if you're loading files into Pulp from a different area of the file system, for Puppet files in particular, we offer this SELinux Boolean that lets you enable this if you're doing that use case. We don't enable it by default because we don't want to allow our process to do that because most of our users don't do that. But we have a switch that lets you enable the SELinux, this particular Boolean that we as policy authors have made. And it lets you basically enable a whole group of allow statements. If you look at things like HTTPD, they have a lot of Booleans. And so if something is not working well, you probably should check the Booleans to see if maybe this is a use case that isn't enabled by default and that you need to enable. You can enable them with this set SEBool option here. There are some examples like, oh, HTTPD can make a network connection, for instance. Oh, this is a much better example. HTTPD normally doesn't make network connections. It receives network connections, right? But if your web code also needs to make network connections, then you should enable this Boolean. So that's a look at what the Boolean concept is. Okay, troubleshooting. Check the Booleans. So that's the first thing I would probably do. Maybe one needs to be enabled to allow your use case to work. Maybe it's a perfectly normal thing that you're doing, but you just need to enable the Boolean. And if you take the module and convert it to CIL, you can actually see the Booleans listed. And at the end here, just in like 1 minute, or maybe 5 minutes, which will be done then, we'll actually see what a CIL output looks like, and you can actually read the Booleans there. You can also read them in the documentation. Any project that's doing it well, or even half well, is going to have some documentation on the Booleans that they ship with. You can temporarily turn it into permissive mode. This is a really great thing that you can do temporarily. Don't leave it in permissive mode. You can also check 3 things. I recommend checking 3 things. Verify that the inspected policy is installed. Sometimes, I mean, it's a C-based compiled thing, and sometimes it might not match the version that it needs to load into. You know, strange things happen. So make sure that the expected SELinux policy is installed. Then verify that the process is running in the expected domain. So, you know, PS with the capital Z, and you can look at the process and say, oh yes, this looks right, or hey, this didn't seem to transition into the process domain that it should be, so let me look into why that happened. And the other thing I would say is verify that the file contexts are set correctly. And again, if you decompile the policy into CIL, you can see that. We'll look at that here in a minute. You can also look at the upstream or application source where they built their policy from. But I kind of like doing it from the running system because then you know what it is versus the upstream source, which you then have to make sure you have the right version and get all those things right. It's a viable technique, but I like doing it from the running system. Sometimes apps fail with no AVC denials. This has happened to me. Has this ever happened to anybody here? Okay, one person there. 2 people there. Okay, great, so it's 3 of us. This sucks. And you'll know you're experiencing it because when you have SetEnforce 1 running and you run your app, it doesn't work somehow, and you say, is this maybe an SELinux problem? Let me move it to SetEnforce 0, and it does work. And then you say, oh, okay, well, let me go check the SELinux logs, or maybe you did that from the first start, you probably should. And there are no AVC denials there. And you're like, what? So there are these things called don't audit rules. Applications have these different code paths that are normal expected failures. For instance, like if you don't have the Boolean enabled, for instance. Or it's a code path that's just normal, and the application authors and policy designers, for whatever reason, feel like it's a normal use thing and something that they don't have to record. Well, sometimes they get it wrong, or maybe your environment's a little different. And so you can disable the don't audits. Basically, it says, I don't care what the policy people said, I want to see all the stuff. And so if you're in this situation, disabling the don't audits is a great thing to do. Working around problems, so report issues to your upstream projects, to the application developers. And what you want to do is you want to determine if an issue is environmental, if it's a code defect, as in the application is wrong, or if it's a policy defect, the policy is wrong. Filing an upstream bug is going to help you get information from people who have experience to sort that out. So you want to establish that. That's kind of the first thing you want to do. If it's a legitimate incompatibility between the application and its own policy, which basically means it's not your fault, then I recommend doing this. You can reload the SELinux modules. So all these policies that are stored and compiled, you can tell the LSM, the kernel level module, to reload. And this creates a reload point, which is useful, as you'll see in a minute. So you create a reload point with this SC module -R. Safe to do on a running system. It'll just a command that runs and comes right back. And then you can set the application to permissive mode and restart the application. And you can trigger the AVC denial again. Maybe you have to use the application in a certain way for that to happen. And then you use this audit to allow tool. And this will show you the allow rules that would have allowed those things to run. So the reason I recommend this process is because if you don't put it in permissive mode, you'll end up doing this probably over and over again because of the first denial problem. And if you don't do the -AL, A says all, and L says since the last reload point. Because you could have a bunch of ABC denials from like the past 20 days or something like that, and you don't want to allow all those. So that's why it's important to create a reload point just before you reproduce your problem. And you'll get something like this. Thank you. You'll get something like this, which says, oh, well, if this is an allow rule that you should run into your policy. But the question is, how do you get this into your policy? Well, you can do it. You can have audit to allow actually create and compile a policy that you can then install on your system. So this is kind of like an aftermarket policy that you as an administrator are creating. And you use this -M, capital -M, to create a policy called mycertwatch. And you can install it with SEmodule -I. And if you see what it created, it'll write this .te file, which is where the actual statements are contained. And then if you compile it, it'll make a .pp file, a policy, is a policy, compiled policy file. So if you come next week to the hack night, then we're gonna actually make we're gonna do a lot of this kind of stuff. We're gonna write some policies. All right, so what if your ABC denials are coming from multiple processes? Well, you can filter them with grep and feed those statements into audit to allow. So this is a way to make sure that you're only allowing the ABCs that you expect, and you can always look at the .te file, which shows the raw policy statements there. You can apply these using CIL as well. So you can, for instance, extract the PP file from a running system. And this example is not quite correct. It should say sudo SEmodule HE and then the name of the module here. So this, I gotta update this system, sorry. You can convert it to a CIL file from the PP file. So this was the PP file that was dumped out, and you can convert it into this .CIL file. And you can edit the CIL file as necessary, and then you can reinstall the CIL file like that. All right, the last thing that I want to do. This is the first time, I appreciate all of your speed about this, because this is the first time I've given this presentation. I've been working with SELinux for a while, but I really had no idea how long it would take, so I appreciate you bearing with me.
Plus the font size.
Yes. Okay. Let me just come in here. Okay, so you have to have sudo to read these things in targeted mode. So you can see there's a whole bunch of these here. So what I'll do is I will say we're going to look at like Wireshark, for instance. So I will tell SEmodule, give me a dump of the CIL file output that is all the instructions and associated knowledge associated with the Wireshark policy. And SELinux has these priorities, and it says, oh, I couldn't find it at priority 400, so let me do it at priority 100. And if you look here, you'll see that there's this wireshark.sil here. And this is a bunch of statements, and this is basically an SELinux policy, and you can come learn more about these next week at the Hack Night. We're not going to go through these, so this is more of an impressionistic look at, this is a very complicated policy. We'll look at some simple policies next week. And after all these type attribute definitions, you can see some of these allow statements. So these might look a little bit familiar. Oh, allow Wireshark T to have these permissions on the directory labeled Wireshark home T, and so on and so forth. And if you go to the bottom, at the CIL it puts at the bottom of the output format the file cons. So this is just like the FC files that we looked at earlier. So we can see, oh, well, do they have the right label, or what are the expected labels? CIL will tell you that. And then just a little bit further up are the Booleans. So for instance, there's this Boolean called X server clients write X SHM. I don't know what that does. But it's a Boolean that you can enable with set SEBool. So that is all my time. I've actually gone over my time. So I will just thank you all so much, and I will hand it back to Jeremy in the back.